Okay, so moving on with martingales. So last time we introduced the definition and then gave some examples of what martingales are. So just remember that a martingale is a process, is a stochastic process. Particularly a martingale is defined with respect to a filtration, meaning that there's some process. Also, we have this filtration, which is a sequence of increasing sigma fields with respect to which our process is measurable at each time. And we think about that as the information that we are accumulating as the process evolves. And for the process to be a martingale, it satisfies this condition right here, saying that where we expect to be at any point in the future, given where we're at now, and given the information we have about the past, um, well, is exactly the same as where we are now. So we don't expect to go up, we don't expect to go down. The One of the main theorems for martingales historically is called the optional stopping theorem, or the optimal stopping theorem. But what this is defined as, or what this, and this is what we're going to prove here in this class. So just to state the theorem that we're interested in, is if we let x be a martingale and it's going to be a martingale relative to so it's an Fn martingale, and let tau be a stopping time also relative to the filtration, and I'll define what that means in a second. Then for all n, the expected value of the process x at the stopping time cut off at n, so the tau minimum with n is just the expectation of the initial state. This theorem is also extends to sub and super martingales, which we haven't defined yet. So we'll leave that for later. But that's the theorem that we want to prove here today. And in order to do that, I want to introduce I have to introduce some terminology and some new concepts, and then we're going to prove that. So first is just to recall. So when we talked about random walks and Markov chains, previously we talked about stopping times as being random variables that are measurable with respect to the past in some sense. And so what we define here for martingales is that if we have a process and a filtration, then a random variable tau is a stopping time relative to ft, relative to the filtration, or you could just say it's an ft stopping time. if the events tau less than or equal to t are measurable with respect to ft for all t. Okay, so this is just saying that the information in the filtration is enough to determine whether or not the stopping time has happened yet by time t. Okay, and so this is equivalent, at least in the case where in the discrete time it's equivalent for tau n, tau equals n to be measurable with respect to fn for all discrete times. Okay, and just to see why, first to show that, let's see, first to show one is that we can express tau equals n by the set theoretic difference between tau less than n, tau less than or equal to n, and tau less than or equal to n minus 1. Okay, so this is showing that showing in the direction that the definition implies that tau equals n is measurable. Well, this is measurable by definition. This is measurable with respect to fn minus 1 by definition, but it's a filtration, and so this is measurable. In the other direction, we can define, if we assume that this condition holds, we can define tau less than or equal to n as the union finite union of these events, that it's equal to any specific value less than n. Of course, these are measurable with respect to their respective fields, and it's a filtration, so this is satisfied. Okay, so it's just a little bit of review there about how we think about stopping times. Okay. Now, when we work with these, so what we want to do is we want to prove the optional stopping theorem, and there's a couple of important concepts to introduce for doing that, and those are there's two particularly important concepts, which are Martingale difference sequences and predictable sequences. Okay, so I've talked about this before, but the motivation, one of the primary motivations for studying martingales, and particularly where the optional stopping theorem, why it's so important historically, is we can think of the stopping time tau as a strategy, a gambling strategy. So if we were playing a game and I were to decide that, well, I'm going to stop as soon as I see this pattern, this particular pattern. Once this particular event happens, I'm going to stop. And so maybe that pattern would be that I will stop as soon as I am up $1. And so if I could guarantee myself to reach that stopping time, then I would be guaranteed to make $1. And so that would be a profitable strategy. What the optional stopping time theorem says is that there is no such strategy, at least in finite time, right? So this specifically holds in the way that I'm writing it, and it can be generalized for bounded stopping times. So if I want to play for a finite amount of time and guarantee myself to win $1 in a fair game, I can't do that according to the optional stopping theorem. Okay. So the two. So the way that we're going to actually prove this is we're going to express this particular quantity, the process evaluated at this stopping time, we're going to express this in some sense. We're going to think of it in terms of a gambling strategy, or the outcome of a particular gambling strategy. Okay. Should also point out that we've talked about this before. If tau is an ft stopping time, then tau min n is an ft stopping time for all n. Okay. So this here is a stopping time, tau min n. Okay. Okay. So let's let xn be a martingale and define psi n for each n to be the difference between successive values of the process. Okay. Okay. So the sequence psi is defined as a difference of successive first differences in the Martingale sequence. And so it's called a Martingale, this is called a Martingale difference sequence. And a few properties that we can immediately show about Martingale differences. Let's see what I wanted to show here is, first of all, some proposition, okay, is if we let psi n be a Martingale difference sequence for an Fn adapted Martingale, then first thing we know is that psi n is measurable with respect to Fn for all n. Okay. And the conditional expectation of psi n given the appropriate sigma algebra Fn minus 1 is 0 for all n. Proof of this is straightforward, but just to be clear, if we assume xn is an Fn Martingale such that psi n is the Martingale difference sequence defined from it. So calling something a Martingale difference sequence implies that these items exist. Then first of all, by definition, we have a difference of two quantities that are measurable with respect to Fn, and so it's a measurable combination of Fn measurable random variables, and so it itself is Fn measurable. And secondly, the conditional expectation by definition, is the difference, conditional expectation of the difference. Now, xn minus 1 is measurable with respect to fn minus 1. And we first use linearity of conditional expectation. And now the first term, we use the Martingale property. Second term, we use the fact that xn minus 1 is measurable with respect to fn minus 1. So the difference is 0. Okay. Okay. As a corollary, we can, as a corollary, let psi be Martingale difference let's see. No, we want xn to be a Martingale relative to the Martingale difference sequence psi n. So what I mean by this is that xn is the sum of the first n Martingale differences plus sometimes plus x0. Okay, and so psi n is the Martingale difference sequence for xn. Then the first thing we have, and we automatically have this. We already know this for Martingale, so we can. I won't prove this again. Then we have the expectation stays the same for all time points, and also if the second moment is finite. If the second moment is finite, then the Martingale difference sequence values are uncorrelated. Okay, and so what that implies is that the second moment of the process is the sum of the second moments of the Martingale difference sequence. Okay, and I'll only prove the second part of this just to illustrate. By definition, okay, expectation of the square, the second moment, is the expectation of the sum. Okay, yep. Which breaks up as the expectation of the sum of squares plus the expectation of the sum from j equals n, k not equal to j of psi j psi k. Okay, so first thing is what I want, although I want to bring the expectation inside, which I can do. It's just a finite sum. Second thing I can rewrite as twice, and I get a sum. J equals 1 to n, k greater than j. Expectation psi j, psi k. And what I need to show now is that this second term is 0. The second term is 0 by the tower property. We can write here for each k, we know that k is bigger than j. K is strictly bigger than j. So one thing that I can do is I can write the expectation. I can write this as the expectation of the conditional expectation of psi j, psi k, given fj. And if I do that, this is by the tower property, if I do that, psi j becomes measurable, but then I'm left with initial expectation of psi k given fj, which we've already shown is 0, and so this part will be 0. Okay, so that's property of a Martingale difference sequence. Okay, and Martingale difference sequences come into play because, for reasons we'll see in a second, but this gets us to the gambling the gambling interpretation of thinking of a process as our changes in wealth, the differences between our wealth at each time. Those are the results of a Martingale. Those are or can be represented as a Martingale difference sequence. Okay, so the second key notion that we need here is that of a predictable sequence. Okay, let me put this here. So a predictable sequence Z1, Z2, etc., relative to a filtration Fn is a sequence of random variables such that Zn is measurable with respect to Fn minus 1 for all n. Okay. So if you think about what we're discussing here in terms of the key concepts that we have here is we think about having time, okay, and we have discrete time points 0, 1, 2, 3, and so on. And what's happening is that the process is evolving. So there's a process evolving. This might just be a sequence of coin tosses. Say, sequence of coin tosses. That's generating for us that's a sequence of coin tosses. We have a sequence of coin tosses, say. We have a martingale in this case. Let's say it's a fair coin and we win $1, lose $1. So we have our martingale, Z0, Z1, Z2, Z3, etc. And what the martingale is how much money we have at time n for each n. And the predictable sequence that we're interested in, the predictable sequence, actually let me fix my notation here. This is no good. Okay. Let me stay consistent with the outcomes of the coin tosses are going to be, so we have coin tosses, and what Z is Z is a predictable sequence which is how much we bet on each round. So when I'm placing my bet for the third round, I can look back on, I know how much I'm going to bet based on what's happened in the first 3 tosses. 0, 1, 2. I have to be able to determine my bet, because if I can't, then I don't know how much to bet, then I can't play this game. Okay, so this is a predictable sequence, and then the process that we're actually interested in is going to be our wealth, or our wealth process, which is determined by the outcomes of the coin tosses and how much we bet at each round. Okay, and so what I'm going to define here, and I'm going to end up using different letters, so I don't want to interfere. So let me write y1, y2, y3. Determined by the outcomes and the bets that we make. Okay, so this leads to the concept of what's called a Martingale Transform. Okay, so what we have is we're going to have a process that is a Martingale. In particular, it's actually going to be a Martingale difference, and we're going to determine a Martingale difference sequence and a predictable sequence, and from that we're going to define what's called a Martingale transform. So our wealth in a game of our wealth process in a fair game is what is an example, and it's the example we'll work with of a Martingale transform. So if we let xn be a Martingale, be an FT Martingale, and psi n be its Martingale difference sequence, and Zn be a predictable sequence, then the Martingale transform is defined by, is a process, and the notation I'll use is Z transformed by X given by, so Z, the process at time n, is equal to some initial transform plus a sum over the first n results of the process of zk times the Martingale difference sequence. So what's going on here, if you look into our picture, is that we have a, so just to illustrate, what we do is we have a sequence of outcomes. So again, this is time. And what happens is on each outcome there is a head or a tail. +1, -1, -1, +1, which indicates whether we win or lose our bet. Okay. Well, not at time 0. We'll just leave this. Okay. So here we're just going to start with some fixed amount and some initial state. But we toss the coin. We get the Martingale difference sequence. So this is the sequence. We have a Predictable sequence, which tells us how much we're going to bet in each round. And this is exactly, when we multiply these together, this tells us, well, if we bet this much in this round and we lost, then we've now lost Z$1. We've lost an additional Z$2. We've won back Z$3, and so on. And so this part of the equation, this part of the definition tells us how our wealth has changed as a result of the outcome of the process. Okay. All right. And so the first thing to show is that proposition, if we let Zn be a bounded, predictable sequence, then its transform, then the Martingale transform, is itself a Martingale. Okay. And this is easy to show. This is very easy to show. We just follow the definition, the conditional expectation of the process at time n, given n minus 1. By definition, this is equal to the process at time n minus 1 plus Zn psi n. Now we use linearity and measurability, and let's see. We use linearity to get this. And now what do we have? We know that Zn given Fn minus 1 is equal to Zn given Fn minus 1 is predictable, and so this comes out of the conditional expectation. But now I have a Martingale difference sequence in the size, so it has expectation 0. So this is Zn times 0 equals 0. And here I have the Martingale transform at time n minus 1, which is a function of the process only up to time n minus 1. So this is just the transform at n minus 1. So it shows that it's a Martingale. In doing this calculation, I realized that I misspoke over here, is that I shouldn't be conditioning on J here. No, I could do that. It's fine. Never mind. Okay. Okay. So a Martingale transform is a Martingale, and that's what we're going to use to prove the optional stopping theorem. Before I do that, though, I want to state the theorem in some generality. So what I'm going to do is I'm going to actually introduce and define the concept of a sub and super martingale. So remember that a martingale is a model for a fair game, a game in which you don't expect your money to grow or go up or down over time. A sub and super martingale are games that we do expect to either win or lose over the long run. So a process, so xn is a sub martingale or a super martingale, and sometimes I'll use little s for sub martingale, big S for super martingale, if the conditional expectation of xn plus 1 given fn, so again it's a sub martingale relative to a particular filtration, Submartingales are expected to increase. Supermartingales are expected to decrease. So that's the definition. And there's certain things that we can do with submartingales and supermartingales. Well, really, a submartingale is submartingale is the negative of a supermartingale. So you can study anything about submartingales by studying for supermartingales, and a process is a martingale only if it's both a sub and a supermartingale, because both of these conditions have to be satisfied. One example that I'm going to give is to show how to generate a submartingale from a martingale. And the way to do this, or one way to do that, that turns out to come up every once in a while, is to take a convex function So if we take a convex function and it has to be convex such that the expectation of the process xn is finite for all n, where xn is a martingale. Okay. Define a new process as the transform of xn through phi at each time. And, claim is that this new process is a submartingale. And to prove this, it's really just an application of Jensen's inequality. Okay, so proof So recall Jensen's inequality. Well, we didn't cover Jensen's inequality last lecture, so let me just recall Jensen. Okay. So Jensen's inequality says, first of all, if phi is convex. So if phi is a convex function, then the expectation of phi of the random variable is greater than the function evaluated at the expectation of the random variable. Okay? And similarly for a conditional expectation, the conditional expectation of phi of x given y is greater than the function evaluated at the conditional expectation of x given y. And the picture is very simple. You've probably seen it before. The idea is that if I have a convex function, it looks like this. The function evaluated at the mean, for example, is here. So this is the mean. This is phi evaluated at the mean. But the mean of the function is going to be along this line, and the mean of the function is greater than the function at the mean. Okay. So now, in this particular problem, or in this particular claim, we're taking the conditional expectation of phi of zn plus 1, so this is phi of n plus 1, given some filtration. But by Jensen's inequality, this is greater than or equal to the function phi evaluated at the conditional expectation of n plus 1 given fn. But we assume that x at x was a martingale, so this is just equal to the function evaluated at xn. This is by martingale property. Okay? Okay. All right. So what I want to do next, and then I'll probably stop after this, is I want to prove the optional stopping theorem. So proof. So the optional stopping theorem. And I'm going to repeat it here, is I'm going to let xn be a martingale. No, I'm not going to let it be a martingale. I'm going to let xn be a, let's see, can I fit this on one line? Okay. Yes, I can try this. Okay. Okay. So let xn be a martingale, a submartingale, or a supermartingale. Of course, it's relative to a filtration. And let tau be a stopping time. Then what we have is that the expectation of tau min n is equal to the expectation at time 0 for all n, is greater than or equal to the value at time 0, or is less than or equal to, depending if it's a sub or a super martingale. Okay. All right. Now, I'll show this for the martingale case, although the same thing can be shown by showing that well, it can be left as an exercise to show this for the sub and super martingale case. Okay, so proof for the martingale case. And the way that we're proving this is we're going to express, so the idea is to express this process as a Martingale transform. Okay. So once we do that, we know that Martingale transforms are martingales, and we can use that then to just, well, then this condition here is automatic because, so express this as a Martingale transform, step 1. Martingale transforms are martingales. Therefore, expectation of this equals expectation of the initial state, which is tau min 0, but 0 is the first time, so the minimum of anything with 0 is just 0. So this is actually the process at time 0. So that's the idea. Okay, and so how can we express tau min n, the process at time tau min n, as a Martingale transform? Is we think of it as our wealth process up to a stopping time. So if we're thinking about the stopping time as a strategy when we play a game, and the Martingale transform is how much money we have by playing this strategy, then perhaps it makes sense that we can do this. And it's actually very simple. So what we're going to do is we're going to define x tau min n to be the state at time n of a Martingale transform z transform n for Zn defined as an indicator function. Zn is 1 if tau is bigger or equal to n, and it's going to be 0 otherwise. Okay. So I need to show that Zn is predictable. But what is this saying? This is saying that I'm either going to bet $1 on the next round, or I'm going to bet 0. So I either keep playing or I don't play, based on whether or not my stopping time has hit. Okay, so that's exactly the idea of what the stopping time is. So, okay, so let's first of all, let's just take, without loss of generality, z0 equals 1, so that, okay, so that what? So that the value of the process at time n is just x0 plus the sum up to n of zj times the Martingale difference sequence, which is just the difference of xj minus 1. Okay. Now, zj is either 1 or 0 by definition, and so this is equal to x0 plus sum from j equals 1. And this here will be 1 or 0 up to tau min n. So after tau min n, it's equal to 0. So all these 0 out. And so this is just a sum of the difference. But now this is a telescoping sum. So this equals x of tau min n. So it shows that the definition that we've the definition that we've taken here is actually just a Martingale difference sequence with z0 set to 1. Okay, and z0 will be 1 because the stopping time will always be bigger than or equal to 0. Okay, so the first thing we need to show is that Zn is predictable. And for this, we can just show that the event that Zn is equal to 1 for any n, so Zn is equal to 1 if tau is greater than or equal to n, and tau is greater than or equal to n can be expressed as the, let's see, it is the intersection of the complement that tau equals k for all k up to n minus 1. So let's say 0. Okay. So for all values from 0 up to n minus 1, we look to make sure that tau is not equal to k. And if tau is not equal to k, then of course this is for any of those values, then tau must be bigger than or equal to n. And each of these is measurable with respect to fk, which is fn measurable. Fn minus 1 measurable. And so the whole thing is Fn minus 1 measurable. Okay, so Z is a predictable sequence. And then finally, we just need to prove the key identity, which is this up here. But for this, we simply prove it by observing that the conditional expectation, or the expectation of x at time tau min n, we've already expressed tau min n to be equal to the Martingale transform. But we know that Martingale transforms are Martingales. So this holds. But at time 0, the definition of the Martingale transform is just x0. And so in the case of Martingales, we're done. Okay. So the optional stopping theorem is actually pretty easy to prove. Turns out, as long as we have the right machinery to do so, and the machinery that we used here was the idea of a Martingale transform. Okay. All right. Okay, so that's I think enough for this class, and we're going to continue with Martingales next time and talk about further theorems. Martingale convergence theorem will show an application of the Martingale convergence theorem to prove Di Finetti's theorem, and we'll move on from there.